It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on mechanically stabilized earth walls, which will be delivered by Professor Emeritus Richard J. Bathurst and Ms. Yuli Doulala-Rigby. Yuli is a chartered engineer and a fellow of the Institution of Civil Engineers with more than 25 years of experience in a variety of geotechnical and civil engineering projects. She obtained her first degree in civil infrastructure engineering in Greece and her Master of Science in rock mechanics and foundation engineering from the University of Newcastle upon Tyne. Her work experience includes working as a tunneling engineer for Balfour Beatty AMECJV at the Jubilee Line Extension Tunnelling Project in London, as a geotechnical engineer for Mutual Asia Limited in Hong Kong and as the chief civil engineer for Tensar International, the inventor of polymeric soil reinforcing and stabilizing geogrids from 2005 to present. Yuli is based in Tensar's UK headquarter and for more than 10 years she held the overall responsibility of the Tensar Eastern Hemisphere design team with offices in Germany, Holland, France, Russia, United Arab Emirates, Saudi Arabia, India, Malaysia, Indonesia and China, and representatives in Africa, Australia, and New Zealand. While she is still involved in delivering training, project risk management and troubleshooting, she has recently diverted her focus largely towards business development and educating the industry globally on the benefits of geosynthetics in construction. Yuli is a past chair of the UK Committee of the International Geosynthetics Society, an elected member of the British Geotechnical Association Executive Committee, and has authored and delivered several publications about reinforced and stabilized soil around the world. She is a judge for the Institution of Civil Engineers Engineering Awards, the UK Ground Engineering Awards, and she is the co-ordinator and a judge of the Baroness Platt of Rittle Awards on behalf of the Worshipful Company of Engineers, of which she is a liveryman and a court assistant. She is a registered STEM ambassador and a governor of Welbeck Defence Sixth Form College. She is the first female engineer in the northwest of the UK to obtain fellowship of the ICE in September 2011 and the first non-military engineer to become a fellow of the Institution of Royal Engineers in May 2018.
Good morning, afternoon, evening, whichever is the time, wherever people are that they're watching this. Thank you for your time. I'll stop my video now so it helps with the internet. There you go. Right, so my full name is Chaido Doulala-Rigby, and thank you, Professor Das, and not trying to pronounce it because it's not easy to pronounce. So it's easy for people to just call me Yuli. And the complication of my name is because I'm Greek, so it's difficult to pronounce. So this is the second time I'm presenting this presentation, and I'm delighted and really happy to be given the opportunity to do that, because the first time I presented this presentation, I was asked by the eminent Professor Robert Kerner, and I don't know, I hope some people or most of the people in the audience know Bob, who is affectionately known to his friends. Bob sadly passed away in 2019, just days after I presented this presentation in his honor. So Bob asked me if I would deliver this honor presentation that was established after his name in the series of conferences that the GeoME Middle East has started in Cairo. And that was, I think that was the third time in 2019. And of course, I was delighted to accept. So I put something together. So I said to Bob, what shall I talk about? And he said, well, just talk about your experience in walls and, you know, what lessons were learned. And I said, okay, that's good. That's a good idea. So I put this presentation together. So largely, this is what I will be presenting today. And just a few words for Bob and just for his legacy, for whoever doesn't know who he was. So Bob was a professor emeritus in Drexel University and director emeritus in the Geosynthetic Institution in the US. And he was the most, I think, the most well-known engineers in the history of geosynthetics traditionally. He authored the world's first book on geosynthetics, and he dedicated pretty much his whole life in promoting geosynthetics all over the world. And I had the privilege of meeting Bob for the first time in the Jubilee Symposium on Polymer Geogrid Reinforcement that was organized by Tensar, and it was held in 2009, and it was held at the Institution of Civil Engineering headquarters in London. And we just remained friends because apart from being an amazing brain in engineering, Bob was a humble human being and a very likable personality. So anyway, it gives me a great pleasure to repeat the honor presentation, Bob Kerner presentation, and I'm sure he'll be watching over us smiling with delight that we're carrying on the work that he started almost more than half a century ago, which is promoting geosynthetics. And Bob could not make it to my presentation when it was in Cairo, and it was November 2019. So he sent a lovely video message, as you can see, to introduce me to the delegates and also thank me from doing this for him. So there's a photo of that. And there is a paper for this presentation as well for whoever is interested. It was published by Springer, but I'm happy to send it to you. I've got my contact details at the end. Right, so what are we going to talk about? So what I'm going to tell you about, I'm going to take you back to the beginning where the reinforced soil concept started, because we don't know the history, we cannot move into the future. I think it'll be good I'm hoping that most of you will not have seen the history that I'm going to show, because a lot of the things I also found out when I was preparing this presentation 3 years ago. And I've been in this industry for 15 years. So yeah, every day is a school day. Then we're going to talk about the first polymer geogrid origin, the first MSE walls. I'm just going to tell you about the first two ones. And then we're going to move to the main topic, which is good practice and lessons based on my experience as I studied the last 40 years of mechanically stabilized earth walls being constructed. And then we're going to see at non-standard reinforced fills, and we'll see what that means through case studies. We're going to talk how geogrids relate with sustainability, and then of course we'll do conclusions and takeaways for you today. So looking around in any fundamental engineering concept, if you look closely, you'll note that we engineers in many of these concepts, we actually copy nature. So like in this picture, we see an aeroplane that is being designed as a bird lookalike, a big eagle, or a submarine that is being designed as a whale lookalike. And more relevant to our subject today, if we look at the soil strengthening concept and we look at the way that birds form their nests, actually, the principle is very similar. So they use mud and stick to reinforce the mud, soil, wet soil to stay together. And they use like weeds and branches, just like human beings, especially in developing countries. They still use the same technique. They use wet soil or mud with branches or hay or sticks to create these bricks. They're called Adobo Bricks. And they're used to still build houses in many parts of the world. But the soil strengthening concept started way, way before. So the first samples, like I said, if we look closely and we look behind what we see and try to understand how all these magnificent structures are still standing up, the first examples of soil strengthening date back to more than 3,000 years BC in the Ziggurat Walls. At the time, the area was called Mesopotamia, and it's today's Iraq. And the way these structures were constructed was just by woven mats of reeds laid in between sand and gravel. So this is the concept of reinforced soil, in other words. And these ziggurats most of them were forming parts of temples for worship, and they were also called stairways to heaven because they were very tall structures. Then we look into further east, the Great Wall of China. There's a lot of sections of Great Wall of China that they were just built with tamarisk branches, reinforced with local lowest soil, which is also known as wind-blown dust. And this is one of the beauty of reinforced soil, is that you can put it together using material available where you are. And we'll see about this a little bit later. Even closer, further down the history, in the Roman times, they discovered in a timber wharf forming the Port Londinium, as it was called in Roman times, London. They found this 2-meter high port wall that was preserved in a pretty good, they found it in pretty good condition. It was preserved in the Thames mud, you know, the river in London. And this was just timber with soil, as you can see. And credits, and I'm going to be mentioning Colin Jones' name quite often throughout my presentation, because he helped me a lot to put this presentation together, mainly for the historic part of it, through his book that I think he authored in 1985. But I'm a good friend with Colin, and we're still in good contact. So he was very happy that, you know, I was putting this together, going back in history of reinforced soil walls. Even closer, so 1800, 1822, Royal Engineers, the people that they're very close to my heart, they were pioneers. So General Sir Charles Paisley was the first to build a retaining walls with brushwood, wooden planks and canvas, because he realized and he proved that the inclusion of these layers, the reinforcing layers, result in significant reduction to the lateral earth pressures. Well, there you go. There is the concept of reinforced soil earth in one small paragraph, you know, that conceived by this general of the army back in 1822. He had no numbers and he didn't write any design books, but he used the materials and he built these long-lasting structures. So how did we evolve to modern structures? Well, the fundamental engineering concept, like I said, of soil strengthening, nowadays we call it soil reinforcement, but it's the same, it hasn't changed. So it was conceived thousands of years ago, and it's still to place geo-elements in between soil layers to add strength and stiffness, as we're finding out, and as we've been analyzing further these days. So what changed? Well, the only thing that changed is the Geo Material. So in the olden days, they used natural geo-elements, like we saw, tamarisk, risk branches, brushwood. But nowadays, we use man-made geosynthetics or geo-elements. So we can use, well, steel is used, timber is used, like proper fabricated timber. And of course, we use polymer, like plastic, polyester, we'll see in a minute. So back to Colin Jones' book, the very first example of reinforced soil we have in modern days, it was in 1925 in USA, and we have the monster earth retaining structure, which was like wooden ladders. I hope you can see my cursor, that they go behind the wall with a very light type of facing. Then in 1930s, the corny retaining wall came along, which was like short ties, metal ties with anchors, and selected stone fill, and with concrete precast facing at the front. But as you can see, the way they place this concrete facing, the one inside the other, is purposely so they can allow movement, because they already understood, these people that they started the concept of reinforced soil, that it's a flexible structure. So whatever we do, we need to be ready for it to somehow breathe and move, okay? The third example, which is perhaps the most well-known, and I think most of the people in the audience would have heard, it was the Vidal's invention or evolution in 1960. So he used the U-shape, he used flat iron strips reinforcement connected to U-shaped steel metal channel facing. But he actually commercialized the concept, and he patented this MSE wall as Rainforest Earth, and I'm sure everybody knows of this system nowadays. It's you know, with concrete facing. Oops. And the last one, that going back to history, which again it's probably a lot less known, is another method. It's called the York method, and this was developed in 1973. Again, Colin Jones was pioneering the development on this. And it was just hexagonal concrete facings reinforced with glass, and actually the reinforcement strips behind the facing were also reinforced plastic with glass. And then in late 1950s and early 1960s, a new material appears, and that's extruded polymer. So for the first time, we started seeing this way of this new man-made material, the extruded polymer. And the first use of it was just to make commodity nets, as you see, they're still pretty much in use, to carry groceries or to protect bottles. And this technology was first invented by a company called Netlon. And I think in many parts of the world, or for the elder people in the audience, will remember and recognize the name Netlon. And while these meshes were developed, and there was a lot of research and trial and error, there was a heavier net that was developed through the same was the same manufacturing method, extruded polymer. But the mesh that they developed was slightly thicker, and the Japanese found out about it, because they always do, and they looked at it and they thought that this will have some sort of engineering properties, or will improve engineering properties, and they used it for the first time and very successfully utilized it in Japan in 1970s to improve the bearing capacity in Narita Tokyo International Airport. And there's some photographs of laying this Netlon mat in Narita Airport, and they found out that it performed really, really well. So the person who invented this new material, extruded polymer, was Dr. Brian Mercer. And Dr. Brian Mercer was British, and he was born in the northwest of England, where polymer geogrid was also born. And he was also a good friend with Salvador Dali. And there is a painting that we see that Salvador Dali did of Dr. Mercer. And Dr. Mercer has donated this painting to the Royal Society in London, which he was an honorary fellow. And it's hanging to a room that they named after his name, the Mercer Room. And there's a photograph here of Dr. Mercer explaining the properties of the geogrid to Salvador Dali. So if we were in a room, I would ask you, who is the father of soil mechanics? And everybody involved in geotechnics would know that is no other than Carl Dezaki. But now you know, if I ask you who is the father of geogrids, that's Dr. Brian Mercer. So following the success of the Netlon mesh in Narita Airport, Dr. Brian Mercer saw a gap, because he was a great technologist, but a great entrepreneur as well. So he saw a gap in the industry, or in the construction industry, and he focused his interest and his efforts, and he joined up with a group of mechanical engineers and chemical engineers, and he came up with the Tensar process. So they used polymer, and not only extruded it, they punched it and they stretched it. And the stretching is the procedure in the manufacture process that gives the geogrids the strength, because it orientates the molecules towards one direction or multiple direction, which is what it gives the geogrids the strength and stiffness as we know them. So 1978, a brand new product is being invented, the Tensar, and he renamed it. He moved from Netlon to Tensar. And these first two geogrids were invented. And at the time, they were not called geogrids. They were called plastic meshes, because nobody quite knew what they were. Until 1982, where Professor Peter Roth from Cambridge University, he came up with the word geogrid. So the first time the word geogrid was invented, it was by Professor Roth from Cambridge University, because when Dr. Mercer invented this new product, polymer geogrid, he didn't exactly know what he can do with it, or how engineers can design with it. So he went to the best universities at the time, and this is a legacy we carry on to this date. We still go to the best universities or research and laboratory houses, and we keep on evolving, and we keep on finding new ways or new applications for our products. So anyway, so he went to places like Cambridge and Oxford, Strathclyde, places in America and in Australia, many universities around the world, to find out how these geogrids perform. And like I said, true to his legacy, Tensar itself carries on innovating, and in 2007 we invented the evolution of the square geogrid to the hexagonal geogrid, but we're not going to talk about this today. So great invention those days. Imagine going to a civil engineer in 1980 and tell them you can build bridge abutments with plastic. People, the engineers would just look at you and raise their eyebrows and say, I don't believe this. However, we did manage to start convincing the important people in the UK. So we got the royal approval, and here is, and today is a somber day, or this week it is in the UK, as today is the 1 week since Her Royal Highness Prince Philip has passed away. But this is happy days, and in memory, Dr. Brian Mercer meeting Prince Philip and demonstrating how net-long grid works. So like I said, how did an unknown entrepreneur from Blackburn convince the world? Well, there were pioneers and open-minded people and visionaries that we got the support. They saw the benefit of these products and the potential. And one of these great supporters, Richard Bathurst, was one of them too, because he saw the feasibility of these new products. But a great visionary and supporter was Professor Colin Jones. And I am very, very, I had a few various conversations in the build-up of this event with Dr. Pratha and different people, academics we know in the industry, and people that taught him, or the books that he's been taught from. And my great memory of my student years is Professor Colin Jones, because I had the privilege to have him as my professor at Newcastle University when I did a master's degree, as Professor Das said at the beginning. So Colin Jones took these geogrids in 1980 when they became available to the industry. But remember, at 1980, there was no design method, so nobody really knew what to do with them. But Professor Colin Jones kind of, the way he understood it, he developed a design method, and he designed the first wall. And the very first wall that he was designed and built with these products, with the uniaxial geogrid, the first MSE wall with polymer geogrid, was in Yorkshire, which is where Professor Colin Jones was based at the time. He was the chief engineer for the local authority. And they had an existing railway embankment. It wasn't high, it was only 2.5 meters high. But as you can see, it was eroding away, and you can see the sleepers hanging over. And this railway was carrying all the mine waste from surrounding coal mines in Yorkshire, because those days coal was the main source of energy. So they had obviously to remediate this embankment, because that's what it was doing to the tracks up above. So it was, it was causing a risk of derailment, as well as slowing down, the production and, the whole cycle. So what Colin Jones did, he came up with a fantastic idea. Remember, from the beginning, we mentioned that you always have to remember that they're flexible structures, and you have to allow and cater for some sort of movement. So in this particular case, Colin Jones designed as a reinforced fill. They actually used the mine waste, which is soft and wet and not particularly strong, as you know. As a facing, he used these precast wall units, but the clever bit came in the way that he connected the facing with it. And of course, here he reinforced the mine waste with our geogrid. You can see the Tensar geogrids, but the way he connected them to these steel wall brackets Why did he do that? Why didn't he cast them? Because he knew that this material will move. So he allowed for controlled settlement. So this, our geogrid could slide down as the mine waste is settling in time. So that was very, very clever. And of course it worked. And also at the base, he used, because the existing foundation soils were not brilliant either, so he used the same material, this Netlon heavy mesh, that they used in Narita Airport and to enhance the bearing capacity of the existing soil. So there you have it. That was the very first, and he used timber fender units, because what would happen here, let's go to the next one. I thought I had a photo of the finish, never mind. So what was happening was that the wagons would bring in the coal mine waste from the surrounding mines, tip it over here, and big lorries picked it up and go and disposed it off safely. And this was the reason why he used the timber, so to protect these precast wall units. And there is a paper on that I co-authored with Colin, and it was published in Berlin, I think in 2014. At the same time, so that was the very first wall, civilian wall, I should say, or for civilian purpose for railway. At the same time, the Royal Engineers, again, they heard about this product, and they too realized the ductility of this product and the flexibility that an MSE wall structure has because of this material. So again, with no design method, and Colin also worked with the Royal Engineers, Professor Johnson. He helped them design and build these walls. And these walls, the purpose they were built, what is in this building is ammunition. So they use these walls to protect as ammunition blast bands. So in case something went wrong and there was an, unplanned or accidental explosion, they contained the explosion, because any shrapnel would be nicely absorbed and contained within the flexible tensor walls. So that was in 1980, and this is 2019, where I had the privilege to go and visit this same wall. So this is the building, there's the building, the back face of it, and this is the slope, which is still standing up 40 years later, absolutely no problem with it, nice vegetation. So very, very good testimony of the resilience of these structures. And from these humble beginnings of almost 40 years ago, nowadays we moved to structures that Dr. Mercer would have never dreamed of, and that we would ever reach that high. So this is our highest wall, that's Tensar's highest wall, and one of the highest MSE wall in the world. So it's 60 meters high, it's a tiered wall, as you can see. So it's 20 meters, 20 meters, and 20 meters. It's in the Middle East. It joins Fujairah and Dubai, and it's not just a wall, it's an embankment. So we'll have a look at, we'll see more of this later on. But the actual construction is pretty much similar to where we started 40 years ago. So the way that this wall is built is just dry laid, and that's why it's so fast and easy to build. So there's the geogrids, good granular fill, compacted, and just modular blocks at the face, dry laid. And the geogrids, they just connect in between the facing blocks to a blue connector. So they create a very nice mechanical connection, which is actually fantastic in performance, especially in earthquake regions. But that's a different subject altogether, so we don't have time to talk about it today. Recognitions of the Tensar polymer geogrid, because it was the first. The Royal Society, many awards, both to Dr. Mercer as well as to Tensar and Netlon, and also the Royal Academy. And for whoever follows, which I'm sure many of you do, you know that the logo has changed recently of the Royal Academy. And our invention and Dr. Mercer got the highest and the highest and most prestigious national prize from the Royal Academy of Engineering, the MacRobert Award in 1984 for this engineering innovation. So this is the letter of the MacRobert Awards nominated or awarded to Dr. Brian Mercer and Netlon and Tensar. But sadly those days, the photographer had only one chance to get it right because he couldn't see what he was taking, to change it or take another one. And this is a photograph of the award ceremony. There's Prince Philip again, and there's Dr. Mercer. Sadly, in his one chance to take these photographs, he was standing behind Prince Philip. But as you saw before, he had many, many other chances to meet Prince Philip. And because of the week that we're going through in the UK, I just thought to, like, as a tribute to the big man, His Excellence, the Prince Philip, and I don't know how many people know that his involvement with engineering. There's been quite a few in social media and LinkedIn, but whoever did not know, Prince Philip was fundamental in the establishment of the Royal Academy post-war, because he wanted to connect all the different engineers, mechanical, electrical, chemical, civil, and to rebuild England. And he came because he was a very big supporter of engineering, and he strongly believed that engineers are, are amazing, amazing people. And he quoted this immortal quote that I use in all my STEM events. Professor Daz said at the beginning, I'm a STEM ambassador, and I'm very, very passionate in talking to kids about engineering. So Prince Philip said, everything not invented by God is invented by an engineer. And he said that in 2015 in an interview in BBC 4, Radio 4, with BB executive Lord Brownie. You can Google that interview and read it for yourself. But yes, rest in peace, Prince Philip, and thank you for your support. And that's I'm very, very happy that I'm able to do this tribute on air. So back to our geogrids. A recent very prestigious award that we got, and very, very proud of it, in IC 200. And again, I hope most of the people in the audience caught up with celebrations of the institutions of civil engineers, the oldest engineering institution in the world that celebrated 200 years in 2018. So they went around the world, and I think a few projects from Australia and from India made it to these 200 projects. But our geogrids were included too. And the way that IC recognized our geogrids were like the innovation that revolutionized civil engineering. So great honor and a great recognition of indeed a product that changed the way we do things in civil engineering. So on to the core part of this presentation, good practice and lessons learned. Let's look at the geogrid material first. So there you go. So what is a reinforced soil wall or a slope? Well, it's geogrid. What is it made of? Of geogrid and soil, as everybody knows. So a little bit of geogrid, but very, very important. So there we go. Geogrids go in horizontal layers within the soil, and they act in tension. We can design for up to 120 years design life. And I hope everybody knows that we design for long-term or creep design strength, because geogrids or polymer is viscoelastic. So we know it's going to creep, but we know exactly by how much, and we extrapolate, and we know exactly the strength that we should be, or residual strength we should be designing them for. And this is exactly why we make them, when it comes to polymer, with high density polyethylene and not polypropylene. Of course, you can do them with polyester too, but I'm not going to talk about this today, because in Tensar we use high density polyethylene uniaxial geogrids for MSE wall construction. So to simply explain this, of course, it's a massive, massive subject, but I hope this couple of slides will explain to you. So we do our creep test, and this is a logarithmic scale on the x-axis and a normal scale on the y-axis. So what we see is strain versus time, which is basically what creep is, so sustained load over time. And we've got an HTP grid to the left, a creep test, and a PP or polypropylene geogrid to the right. And they're both under creep tests at 20 degrees and with the same QC strength. So the ultimate tensile strength, it's the same for the polypropylene grid and for the HTP grid that we are testing. And that's very important. So let's see the load at failure. Let's see what's happening at failure. And let's take this sample. So these are different samples that we test them or we creep them at different percentage of QC strength. And let's look at two of them that they're both at 47%. So if the Q strength, let's say, is 100 kilonewton, so the HDB grid is being tested in creep at 47 kilonewton, and failure occurs in 2 years, okay? For the same QC strength and almost 47% of it, so 47 kilonewtons, assuming that the Q strength is 100, it's just a random number, we see the failure on a polypropylene grid happens in 4 days, and this is absolutely massive. So in real terms, what that means is that when we design just a normal wall, a 5-meter high wall, if we design it with high density polyethylene for 120 years, for exactly the same soil type and supporting the same load, we only need 11 layers of geogrid of a certain QC strength. But if we opt to design with polypropylene geogrid, because you use the creep strength and not the QC strength, for the same performance, 120 years design life, we would need 31 layers of geogrid. And this is just massive because HDPE's got very good creep characteristics, but polypropylene doesn't. And this is exactly why we use high density polyethylene and not polypropylene, even though polypropylene is much, much cheaper. But unfortunately, in many parts of the world, the way they specify geogrids is just by their QC, and that creates many, many problems. And in places like China, they've started witnessing cases like this. So this is geogrid that is being strained and moved. And people think, like academics, that they are involved with expert case studies of a few of them that they failed. And this is the reason, because polypropylene strained, but in China, their standards don't require creep strength. They just require, in the specification, they just specify them by QC strength. So it makes sense, but we can talk about it later, or you can contact me. And there's a few published papers. I forgot to acknowledge, I hope you read it on the slide, that my colleague Mike Dobie has written a few papers on that, and you're welcome to have them. So reinforced fill compliance, what's that all about? Right, so what's the other part of a reinforced soil wall? Well, obviously it's the soil, and actually it's the biggest part of a reinforced soil wall. If we can say, it's like more than 90% in a reinforced soil structure is soil, and a little bit, a very small percent, important percent, but small, are the geogrids. So important in all structures, but in particular for performance, but it's even more important for performance critical reinforced structures like bridge abutments. So the normal way to specify fill in bridge abutments, because it needs to be of highest quality, is quarried, good quality, well graded, preferably angular or crust, granular fill free from organic substances. And this is just just a specification that you would expect to find in a design of a reinforced soil bridge abutment. So what is important when it comes to reinforced fill? Well, it's the fill quality provided on site. So we do the design at the office, we write the specs, but what they do on site is the bit that matters, and the two must comply. And of course, the second good bit that is important is the placement, and we'll talk about it in the next entity. And you would think that they're both common sense. So everything I'll be talking to you about is common sense, but I'll be telling you what happens in reality and how people kind of forget about common sense. Yes, so sadly not always to an engineer. And this is an example of where common sense was forgotten. So this is a bridge abutment designed with reinforced as a reinforced soil. So the green layers are all the geogrids, and this is the facing, which is just modular blocks, 6 meter high, and integral bridge abutments. So the fill has to be of very, very, very good quality. So you have this conversation at the beginning with your contractor or your client, and there's a specification for this project. It was well-graded, angular, granular material with maximum particle size no greater than 75 millimeters, because that affects the performance of the geogrid with the installation damage factor, and a minimum angle of friction of 42. And 42 is pretty much peak. It's pretty much the highest we've ever used, because we'd like to have resilience in our structures, even if the shear box comes back to, in excess of 50. We kind of don't believe that high values, or we choose to stay conservative. So in my experience, I've never designed any wall with an angle of friction of greater than 42. So for this type of specification, I expect to see, if I was to visit site, a material looking like this. But in actual fact, when we visit site of this particular project, we saw this. And I hope everybody goes back, who's watching this, goes, oh my God. And yes, we were in disbelief how they thought that this material can achieve an angle of friction of 42. And what happened in this project, it was very difficult, but we did manage to get these bridge abutments demolished just before the bridge was placed. So it was very, very painful, but at the end, we got to the right conclusion. So the lessons that we learned, well, I would, no matter what, always confirm the design assumptions. Always make sure there's some sort of a side check. I know that sometimes in our industry, and Tensar, for example, we don't take responsibility for site supervision, but we always keep close. We always have connection during construction. So the designer, and some people might say, oh, this is not my responsibility because the fill is under the contractor's responsibility. It's wrong. The responsibility of the designer in health and safety is exactly the same as the responsibility of the contractor. So please remember this and always keep an eye. Always check that what you specified is being used during construction on site. And the other thing, it's very easy to get bullied by big contractors or, I don't know, commercial pressures to say, oh, but if I tell my client that the fill they're using on site is not the right one, I might upset him and they might not give me any further jobs. It's better to say it now and rather than later, because you can avert a disaster. So if you look at it and you don't think it's right, don't keep it to yourself. Talk to somebody and basically use your professional duty to warn at all costs. So when you see something that doesn't look right, voice it, because as an engineer, this is what you have to do. And technical excellence must always, always, always come above any commercial gain. And that's very important. I don't know if any of you have been following what happened in the Grenfell Tower in the UK, the big fire that killed 74 people, I think. Everybody knew that the cladding they were using, there was something wrong with it. But so many people were told to shut up, and they did. And sadly, it ended into a disaster. So please don't be quiet. If you see something that you think is a problem, do raise it. And that was the biggest lesson learned, I think, from all of us from this project. And of course, we stopped it and we averted a disaster. And also with the bridge that failed in Miami, yes, it does make you think to do the right thing. So moving on, compaction and workmanship. Yep, good compaction. I hope, again, everybody in the audience knows why it's important. Of course, it increases the density and the shear strength, and it reduces future deformation. Okay, common sense again. So make sure you use appropriate compaction method and compaction plan that suits the fill material. So when you have granular, for example, is normally vibrating roller. If it's more cohesive, you might use a ship foot. So always be aware of what is being used. Place the fill in an engineering, make sure that the place is filled in an engineering manner. It's normally at greater than 95% of maximum dry density or in accordance to your local construction standards, but as long as it's in accordance to something, and ensure that site-specific testing is undertaken on site to prove the required compaction. And what are the added benefits of good compaction versus bad compaction? And this is the clever lessons learned. It's a nice case study. So these are the big walls that we show in the Middle East that we'll see again later on. So because the project was so vast and there was boundaries different in between different contracts, there was a big boulder that came down the hill. You see how rocky it is, and it hit the wall and it created a massive hole. But did it matter? Well, not really. It did not matter in the stability of our structure, because as you can see inside, I hope, in between the grid layers, you can see the soil being perfectly straight. And that means that the compaction of this soil was exactly as per specification. And the only reason the facing is needed here and in any reinforced soil structure is just a facade and for aesthetics. So the wall can stand up, but in time it will erode due to the weather. So the facing in any reinforced soil structure is just to protect the facing from erosion, the soil from erosion, and that's all. So what we did here, because by the way, this is quite a massive hole, but you cannot appreciate you know, because of there's no scale to see. It was about, I think, more than 3 meters. So instead of taking down the wall and replace it, or the facing, not the wall, the facing, which we'll see in a minute, they just went and put another wall at the front, because remember, this wall is 20 meters high, okay? And this was the final picture. So no problem at all to the construction and no problem at all to the wall, or actually the progress of this wall. So while they were building this plug, the road on the top was being constructed. So no delays and no reconstruction, just an add-on. And this is all because of good construction. But sadly, that's what happens when, not construction, compaction. When compaction is not there, this is another project somewhere else in the world, it doesn't matter where, that actually there was very, very poor compaction. And actually here you can see light. So the whole of the soil just washed out. So this is the drainage that you put behind the face, but yeah, the whole thing came out. So this wall cannot be fixed. It needs to be demolished completely and reconstructed from scratch. So that's bad compaction and bad workmanship. Drainage. And that's the thing, the first thing you are told, and it's drained into your head when you join a geotechnical degree. Drainage is one of the most important things, if not the most important. Water, you know, it's the source of all evil when it comes to geotechnical structures. And there's a lot of advice in the literature of how to deal with water, how to put drainage. So this is extract from Hong Kong Geo Guide 6. And we can see that the drainage layers are there, but none of them daylights to the crest. They're always at a distance. So this must not reach the surface of our structures. You can see the distance is always there. Because a drainage that stops the water is the drainage is there to stop the water going out of a system. The drainage is there to help water come out of a system, but it can let water in if it's badly detailed. And there's an example. So this is a wall somewhere in the Far East. And this is what happened where the yellow circles were. So this drainage, unfortunately, daylighted all the way to the top. It let the water in, excessive water pressure because the soil was quite cohesive. So it knocked the facing off, and you know, it led to well, the wall failed basically, and they had to go and put a massive buttress to reinstate it. A good detailing, like I said, leave at least half a meter from where your drainage finishes to where the wall crest is at the top. So you stop, because if this goes all the way to the top, it becomes a funnel that includes, you know, that welcomes the water instead of stopping and only actioning to take the water from the bank. And another good detailing is, so when you have to provide adequate surface drains for expected flow, so nice crest channels at the top of your walls, and also appropriate crest inclination. So it should always dipping towards the front. There must be some inclination here rather than going towards the back. If you expect ground flow, make sure you've got these chimney drains at the back to intercept the ground flow. And what we said before, this drain must never reach all the way to the top. And the internal drains should be arranged to remain empty always. And of course, the blanket at the base, the drainage blanket, must be of appropriate permeability, because if it's not permeable, it will act as a reservoir and it will soften the surrounding clays. Scour protection. These are the walls. Why is it important? These are the walls that came before the big walls that I said. They're also in the Middle East. They're also in the Middle East, but they're just a single tier and only reach up to 18 meters. So same method, the same construction, modular blocks. And notice, if we were at the audience, if we were face to face, I would ask you what is strange about this photograph, what is missing, but sadly we can't. So can you see? So although they provide scour here because we specified it, they forgot, or the contractor might have run out of material, so they just left it like this. Okay, so what happened then? These walls are next to a wadi, and I'm hoping everybody knows what a wadi is. It's like a natural, a stream course that most of the time is empty, but during the heavy terrain, the torrential rain, it becomes a river. And you can see here how the drainage comes out of this wall, and this is what happens. So where you can see here, so scour stops here, and this has got no scour, the wall, the facing collapses. So what happened was the ferocious row of water washed out the fines at the bottom of this modular block wall, because as you remember, it's all dry laid, and they just fell off. But again, look how perfectly straight the wall is here. And look how perfect is the what is it called? The reservation parapet is on the top. So the wall itself and its stability did not get affected. We just lost the facing, and we had to remediate it for long-term erosion of this soil. Otherwise, structurally, there's absolutely nothing wrong with the wall. And all we did, it was exactly that. We took away all these loose blocks, and oops. Oh, I'm sorry, it hasn't got the final picture. I'll have to send it to you. I'm really sorry about that. So we took these blocks away and we rebuilt it. I think I'll look for it during question time. And it actually looked absolutely perfect. So this project taught us that scar protection is very, very important. That was the lesson learned. And there you go. So in the next project that we did, these massive walls, we made sure that the contractor put not just loose scar protection, but gabion walls at the base. And you can see here as well, and here. And because these culverts, we put the scar protection up to the expected water level in case this wadi was full of water. So Rainforest field variability. Same project, so this is the same project, another section of it. So there's the wadi here, so the flat surface, and these are the embankments. This is the new road, which is the purpose of these two embankments, and this is the one face of the embankment. So if we go to the photograph of here, so this is the lower wall, the lower tier, middle tier, upper tier, so lower, middle, upper, then the road, and behind here is the mirror almost image of the embankment. So upper wall, middle wall, and lower wall, okay? And then the same. So, and at the bottom, you can see these holes, and these are the culvert. Because this whole wall, this embankment is a bridge replacement. So they were supposed to, the original design was a viaduct. So we replaced the viaduct with Rainforest soil earth because it was a cut and fill exercise. So they had a lot of surplus of fill that we used to reinforce with our geogrids and create the new access road on the top. And this is the plan of this. So we can see the very tight contours that would mean very steep terrain, and then the contours that they're very loose apart, which is the wadi, and it defines flat surface. And this is a cross section through here. So this is the back wall, and this is the front wall, okay? And we can see here, there's quite a long berm, and there is the design of this tiered section and the log berm, and we can see that to save money in this project, we used a better quality fill for the reinforced soil block with an angle of friction of 42, like I mentioned, but the retained fill, we used a lower quality fill, so just a 40 angle of friction, which meant that it could be possible that because this is tighter, compacted, and made a denser block, there could be a water pressure collecting through the infiltration. So to avoid this on the top, we made sure that this berm was treated with cement stabilized fill and appropriate gradient on the top, like I said already before in the drainage. So there is a picture of this section, and so there's the lower tier with the 4 openings of the culvert for the water during a storm that during construction was used for traffic, so the lorries could go in. And this is a section through it, so that we gave to that 1 in 10 inclination, and of course you can see the gabion walls, the gabion scour protection, like I said before. And there is a paper for that as well, and it was published in Africa, in Zimbabwe, I think 2011. Non-standard unsuitable fills. So what are non-standard fills? And first of all, why do we use them? Well, we use them because they save cost, carbon, and time, and therefore they make MSE W walls a very, very sustainable option. So when we do use non-standard fills, what do we have to do? We need to have an open conversation with the client at the beginning. We need to screen the site one fill to remove large borders. If the fill is very unusual, we need to do fill-specific installation damage for our geogrids because that affects the performance. We need to do specific shear box test for the unusual fills at the correct rate of shearing. So if it's very cohesive, we know it's going to be very, very slow. So we need to set the rate of shearing at low levels to make sure that what we test is fully drained and not semi-drained. We need to do chemical analysis if we expect contaminated soil, because high-density polyethylene is the same material they use in landfills, and it's okay for chemical attack for pH between 2 and 12.5, but not all soil reinforcement is resilient to chemical attack, or still reinforcement for that matter. So always make sure that it's tested. Adjust rate of construction, because sometimes we need to slow down to accommodate poor water pressure dissipation. Try and make sure how your fill is compacting and how you can traffic it, if it's cohesive in particular and high in moisture. Watch out for drainage, and especially when the fills are like pulverized fuel acid, and we see an example, or chalk, and place the right controls where you are, especially if the climatic conditions are adverse. First example comes from Montserrat in the Caribbean, where we built the old airport was destroyed by a volcano eruption. So we were asked to go and do the new airport, and there was no imported other fill to come through. So we used the site one available material, and you can see the excavation. So they had, the good practice here was they had to screen the side one material, like I said, and remove the big boulders as the guys doing here. And this is the finished picture of the airport and the embankment, and that was about 31.5 meters high. Another example in Malaysia, so a very big landslide, more than 60 meters. The good practice here is that they had to slow down the construction because obviously they use the same material, and because it was highly cohesive, they have to slow down and adjust it to accommodate poor pressure dissipation. And this is the finished product of this. Another product, and this is, I need to give credits to Patricia Escobar from Geosynthetics. They had to do a 14-meter high working platform in the they had to accommodate a raised level with an MSE wall to support a 1,000-ton crane to assemble a new tunnel boring machine to remediate an aqueduct somewhere in the UK. They used cohesive soil side wall material, high in fines. In a sunny day, no problem at all to compact and lay this material. On a wet day, a disaster. So what they did, they put a lot of controls on site, and I'll just go quickly through those. So they had this conversation with the client, and they've organized and said exactly how many plate bearing tests, shear veins, core cutter, bulk density, replacement, whatever, how to do the test on site. And specifically to what they put controls in place. So they said if the CBR on the compacted layer is between 10 or 15 and the relative compaction is just less than 95, so about 85, let the layer be exposed for a few days until, work elsewhere until it dries and settles. But if the CBR is less than 10% on the top of the compacted layer and the moisture content is in the order of 70%, and that would be the case or where there is torrential rainfall, then they would have to go in more severe remediation or plan B. So excavate the first 2 meters and replace with lean mixed concrete actually, and behind the 2 meters, replace the side wall with granular fill until the weather gets better. And there is a paper for this as well that Patricia has written, so I can put you in contact and get this paper. Another good practice we learned is when there is a cohesive and lower standard material that needs to be used, it can be accommodated behind a buffer zone. So what we have done a project that we use 3 meters of granular fill at the front, and we put cohesive material with very low angle of friction, high plasticity behind. And this is a photograph of this project. You can see the granular fill at the front and the very, very cohesive material at the back, no problem at all. And another material that is again is a byproduct, so it's a waste product, you can say, of coal-fired power stations, and this is it's called PFA, or pulverized fuel ash. It's very fine, but it's granular, but in time it kind of cements. It's got an angle of friction typically around 27, and it's very alkaline. So again, if you're using polyester or steel strips, you have to be very, very careful and either factor it down a lot, or you can use high density polyethylene like we do, or we did, and it's absolutely no problem because they are inert to chemical attack. And in this case, and there is standards in the British standard that tells you exactly how you need to place this material and the drainage layers that you have to be around it, and there's all these clauses. And also in this case, because we're working on a flood level up to here, the lower, the good practice that we did, we replaced the lower part of the wall up to the flood level with just free draining granular material instead of PFA. And this is some construction photographs, and this is it. So it was a approach about embankment that we did to a bridge in 2005, 11-meter high. So this wall and this wall here, and you can see the PFA black. This is a final or approaching final picture at the end. And again, there is a paper I authored for this, and I presented in Geo Americas in 2016. Welcome to have this one as well. This is a very interesting project where we were called to see whether we can remediate a landfill in a waste material. So this was a landslide in Wales somewhere in 2005 approximately. So this was a pre-regulated landfill. So nobody quite knew what was there or what was dumped, but it was in a matrix of soil. So the consultant gave us the soil properties. So we designed to reinforce them with our fill materials. They were very highly contaminated: ammonia, COCs, PAH, petroleum, hydrocarbons. But again, no problem at all, because the geogrids, the high density polyethylene geogrids, are chemically inert. And the lesson we learned from this one was that because we didn't know how this material will react in compaction, we started with vibrating rollers, But then we found out that the water was ponding on the top. So they replaced the vibrating rollers with just passages of truck plant, and then that sorted the problem of moisture concentration. So, you know, be open to change and observe the performance and be quick to agile. Well, be agile and switch to a different method when the other one doesn't work. And this is the surface. So they put a thick clay layer on the top to obviously bury the contaminants safely, and they put vegetation, and this is the picture when it finished. And there is a paper to that as well that I presented in a conference in Hong Kong. Use of chalk, again, we in the UK, south of UK, there's a lot of chalk, and the first time we used it was in for the high-speed one, or channel tunnel railing, 8-meter high wall embankments in 2003. And the lesson learned, or the good practice that we adapted here, the chalk was very, very wet. And instead of saying, no, we can't use it, and ask for good granular fill, which would be very expensive and very non-sustainable and non-renewable, we said, okay, we can add some lime. So they've added 2% lime. And then that got rid of the excessive moisture, and we used it. We used the side one chalk. And the last material, that unusual non-standard fill, is called LICA, lightweight aggregate. I don't know if anybody in the audience have ever come across this material. It's basically clay, most of the time like marine clay. And it's fired, it's kiln fired in very, very high temperatures, in excess of 1000 Celsius. And it creates this incompostable porous ceramic material. So being porous makes it very, very light. So normal granular fill, the density is about 18 to 20 kilonewtons per cubic meter. With this material is a quarter of that. The density is about 3.5 to 5 kilonewton per meter cubed. But it's got very, very good shear properties, you know, up to 39 degrees. So typically we would use 37. And because it's light, what it means for us is the bearing pressure that it applies on soil, on the bearing foundations, is very small. And therefore in weak foundations, it eliminates or reduces the need for piles, okay? And it's got a good design life in excess of 100 years. And that's what it looks like. And that's what it looks like in a cross section. It's placed, it doesn't need any particular compaction, heavy compaction, because it's placed pneumatically, and it's compacted just by the traffic of the lorries that bring it on site. And like I said before, very good for weak foundations because it reduces the need of piles. But one thing that you need to be wary, and you need to test it, it's sliding and pull out coefficients with whatever geogrid we're going to use. Tensar obviously used this material, we're the first to use it, and we'd only use this material because we've done all the testing and we know the sliding and pull out coefficients to use. And you can see here one of the applications, and you can see another here. So this is a 12.5 meter high, again, another approach embankment to a bridge. It was done 2016. You can see LICA, and you can see our walls in the geogrid. And this is the final picture, which unfortunately the paper is on the front. There is a paper for that, which again, you are welcome to have. And this was presented in Seoul in 2017. So in conclusion, geosynthetics reinforced soil structures have only been around for just under half a century, but they managed to gain industry's respect and to form their own family of recognized construction solutions because of their simplicity to construct and the significant value that they add in every project. So they lower cost, as you can imagine, because instead of having to import good fill material, we can use what's available on site. They reduce delivery because when we compare them with reinforced concrete, there's no time needed to cure for the concrete because it's dry laid. And of course, they improve sustainability, again, for all these reasons. And sustainability ties in with the UN's 17 Sustainable Development Goals and Paris Agreement in 2015 that many countries, I'm sure including India, signed in Paris in 2015, 196 countries to be precise. And these UN SDGs are coupled with also individual manufacturers' taking steps like specifically for their own production of products. And for example, Tensar, we are very, very proud that since October 2012, all our manufacturing plant and energy that it uses is 100% renewable. So we made the switch because we're very, very cautious towards shaping zero, which is the IC's theme for this year, and decarbonizing our construction, and of course addressing climate emergency that everybody is talking about, and the time for action is now. And collectively as an industry, I hope the examples that I showed you show that the use of MSE walls helps towards replacing or reducing traditional construction methods that they're high energy consuming or CO2 emitting. And like, you know, we replace reinforced concrete or non-renewable quarried aggregate with side-worn material or even waste like PFA. And all this, it's in aim to build resilient infrastructure that leads to sustainable cities and communities. And these are the takeaways of today. This is the last slide. So your takeaways of today is that the specs and good construction practice must be followed when you design MSE walls. Right geogrid material must be used. The right type of, and for the right application of fill must also be used. Appropriate compaction must take place. Good workmanship is very, very valid and important. Appropriate site validation testing, as we saw, and control must be observed at all times. And of course, drainage and scar protection must always be provided. And the last thing we have to do cumulatively as an industry, and this is something that, like I said, I do a lot as a STEM ambassador, is to educate the future generation of engineers and tell them that geosynthetics are sustainable when compared to other traditional walls. And I'll leave you with this picture of events around schools and colleges in the UK that I go and let people use geogrids. This is one of our geogrids, and I make them do little sandcastles, as I call them, like you see, and let them rest a bottle of water, 2 liters water. And you can see the one with the geogrid stands up, the other one collapses. So my special thanks are going, of course, to the organizers of these AGERP lectures, Dr. Partha, Narayan Mishra, Professor Sarat Kumar Das, and Mr. Satyam Tiwari, because without them, this wouldn't happen. The Royal Engineers, of course, for allowing me access to their archives, Professor Colin Jones, Engineer Patricia from Geosynthetics, Lika for giving me information for their lightweight aggregate, Tensar, of course, for giving me the time to do this, and of course you for taking your time or giving me your time to listen, which I took a bit over. And I'm free for any questions, I think. And I'm going to have to look for that picture that sadly escaped.
Let's start with the first question from Howard from Tajikistan. And he says that on the whole, within quotes, in the good compaction example, why not just put on a new facing and then fill the void with low density cellular field rather than build a big structure in front? If worried about the concrete seeping into the field, one would have to put in a bag and then pump the concrete under pressure to expand the bag. Seems like it would have been much cheaper.
I think because the people in the Middle East, they're very proud of the looks, and aesthetics did matter a lot because the client was the Ministry of Works, so they wanted it to look exactly the same. And as you saw, the final picture looks really, really blends well. And that's it, sorry. And I found the picture. So, right, so what we showed before, it was this one, and the next slide should have been this one. So they took down, can you see, you can just about see the 45-degree angle. So where they took all the loose blocks and they put it, we created a specific reconstruction sequence, and they did it, and that's it. So I'm sorry, that should have been there. I apologize, but hey, worse things have happened, but this is what I wanted to look. So yeah, so back to the question of the gentleman that asked, they just wanted to have exactly the same facing. And while they were on site and they had all the equipment in place, you know, they did it like this. But as you can see, you can do it this way. You can just take the blocks away and put them back together again. Yeah.
Okay. Second question is from Jay from ACOM, New Zealand, and he wants to know what is the relative cost difference between the LECA field and the other lightweight fields like scoria.
Good question. I don't know the answer. I know that LECA is much more expensive, and not much more, is more expensive. He's talking about the lightweight field, right?
Yeah.
Yes, and of course the question is relevant because it depends how far it needs to be transported. Yeah, because I think it's coming originally from Norway. But what you have to remember, it's not just the simple comparison between granular fill and LECA, it's about saving on piles. So in this project that I said where they used it in the 12.5-meter project in England, the reason why they went for this material, because the contractor went on site, installed the piles already, and they decided that they had underestimated. So the piles couldn't take the weight of granular fill over 12-meter high wall granular fill. So that's what, so that's like about 240 kPa on the top of it. So it couldn't. So they had the choice to remobilize a new piling rig to come and put the additional piles, or go for a different option. So the cost comparison must not be product per fill versus fill, but holistically for the whole project. Yes. So even if I knew the answer, it wouldn't have been, it wouldn't have been, it's project specific. It's not like generic. It needs to be, it needs to be looked at as a whole project every single time.
This question also came up in the first session. So this points out to the recent MSW collapse in Turkey.
Oh, yes.
The questioner wants to ask, what is your opinion about the failure mechanism?
Yeah, well, I've only seen, funnily enough, I mentioned this last week because I did a presentation for the Institution of Civil Engineers for Saudi, because they've just started their own chapter there, the IC chapter. And I was told to specifically mention that because a lot of the people in the Middle East got very worried, and big companies said, stop all MSE walls. We don't want them because they're failing. And this is so, so wrong. I've just proved to you that we've got 40 years experience of walls that they're indestructible as long as you follow base. It's a recipe. If you don't follow the recipe, the cake won't rise, right? It's not gonna work. So in Turkey, I've only seen the video footage, like a drone, and I saw the still photographs that everybody saw. Like every time we see failures in our structures, it's nothing to do with the product. It's got to do everything with soil mechanics. So to me, first of all, there's no benching from what I see at the back. And I would say it's a rotational failure. To me, I call them as textbook failures. So there is a step at the back and there's a bulge at the top. So to me, it shouts, I think water is somewhere there for sure, because there always is, but it must be the foundation soils were very weak. So the whole thing rotated. And like the whatever reinforcement they use, because I don't know if it was geogrids or steel, obviously it wasn't long enough. So to me, it's probably, in my opinion, it's a combination of not enough geogrid, weak foundation that was missed, because we had a similar failure in China, and the local authority said, no, don't worry about the foundations, we're going to sort it out, we're going to investigate it. Okay. So they said to us, go ahead, no problem, is competent. The same thing happened. The whole slope went like this. So we had a step at the crest and a bulge at the toe. When they went to investigate what happened, they found out that the site investigation they did, it was trial pits that they stopped at 3.5 meters. When they dug further down at about 5 meters, there was clay. There was like a clay with an angle of friction of 21. It was like plasticine, right? So the whole thing, what do you expect it to do? It just turned. And of course, it was fine because it was the local authority said, no problem, we're going to remove the whole thing and rebuild it. And guess what? They put stone columns to remediate the foundation soil. So I think in Turkey, it's got to do with the foundation soils, water, and not long enough, but nothing with the material that they used. So that's my opinion.
The next question is from Charles from WSP Australia. He would like to thank you for your talk. And then he would like to ask, what kind of monitoring and instrumentation would you normally adopt particularly for high walls on not ideal foundations?
Right, not so ideal. If there's an instrumentation is not going to help, you have to have taking this or design for it, you know. So if you expect it to settle, then you should put a mattress at the base to not let it settle, you know, to go. But instrumentation, what we have done in these big walls in Fujairah, we used monitoring points, so like plates on the face. So we monitor X, Y, and Z, so settlement and horizontal deformation in the two directions. In other projects, they use inclinometers at the back. I'm sure Richard must have talked about it in his presentation this morning to see how it works. And I think nowadays, actually, for very big structures, because you did say high walls, we're very excited because we can use LiDAR, you know, what is it called? Help me. Satellite, because these structures are so big, and our walls in Fujairah, there is a paper in the making where we're making a paper which is of these big walls. It's like a sequel to the actual construction, design and construction, to performance. By the time we'll finish the paper, it's probably going to be almost 20 years later with LiDAR construction, because the actual, what is it called, monitoring that we did of the face plates, it finished when the construction finished. So we've got some information, but it's sadly, you can't ask the contractor to carry on, go, you know, and keep on monitoring. But we picked it up now with satellite, and we can monitor the movement. And obviously, you know, there's hardly any movement. So yes, going forward in the future, satellite monitoring, it's got to be the way forward. And we can do it from remotely as well, which is great.
The next question is essentially around if there are any tests to characterize the dynamic friction interaction between soils and geogrids in special applications, such as in case of impacts or blasts.
Okay, so there have been a lot of tests in the early days when the army started using the geogrids to do this, and they also used it for what is it called? Training courses. So they did the bullet arrest bunts, and we also provide this for shooting ranges when people just go and just shoot. Yeah, they do clay pigeon or target shooting. Study as such, I don't think there is. There is some monitoring, and they've done blasting trials through concrete. So they reinforce concrete without geogrids, and they found out that the blast, the cracking, was a lot less when the concrete slab is reinforced with geogrid, because it is so ductile and flexible, than if it's on its own or if it's reinforced with steel. So there is some research, but there's a lot more to be done in this area, you know. So if yeah, are you willing to take on the research? So it is there to be explored, but it's not. We know it's beneficial and it works better, and I don't know whether the army have done any of their own studies, because we wouldn't know, because that would be, you know, part of their classified information. Yeah, so they're a little bit, but not a lot.
Yuli, this is a general question, but perhaps you can talk a little bit on the behavior of geogrids at high temperatures.
Okay, so at high, so what we do, right? So in Tensar, we've got 5 rooms, and we do this creep test that I mentioned in 5 temperatures. So 10 degrees, 20, 30, 40, and 50. Why do we do it in 50? We don't do it because we're ever going to design for a in-soil temperature of 50 degrees. Even in Saudi, I think, which is one of the hottest climates we've ever designed for, I think the in-soil temperature was in the order of 30 or 35. But why do we do in 50? Because remember, ambient temperature and in-soil temperature are different, and there are various studies to say that as you go further into the soil, the temperature drops. But the way why we do in 50 degrees is because temperature expedites deformation. So we take the readings, the creep readings from the 50-degree lab, and we use the super, superposition or something. It's not my area of expertise. I do design. I'm given this. I don't derive. But like I said, everything is captured and there's a paper for everything. So we use the high temperature readings that, they expedite the stretching of the crepe, and we put them and we extrapolate, and that's how we predict the strengths at 120 years design life. So yeah, heat expedites strain, but we know that and we design for that, and that's why depending of where. So in the UK, the design temperature, the strength that we design for is 10 degrees. Mediterranean, we go for 20. And like I said, Middle East or Asia, Southeast Asia, we go for 30. So yeah, temperature makes it faster, but we know it, we understand it, and we design for it. Don't know if that's what he wanted to hear or if that answered the question.
No, I think that certainly is. We have a couple of colleagues as well who wanted to just say you hello and thank you for your presentation.
It was a good long session, Yuli. Actually, I learned. No. Actually, what I learned, in my class, I used to say, first it was the military engineering, every application, then you go for the civil engineering. Because that was a big difference between the military and civil. That's what I called military engineering and civilians. So now civil engineering become electrical, mechanical, computer, and so on. But it was basically civilian engineering, that is civil engineering. And today, after going through a presentation, I was really, happy to know that even that geogrid was also first used in military engineering. Because everybody, it's a philosophy. That is what we try to invent, try to protect ourselves. So that's why this military engineering came. Actually, you remind me of that net learn. Yeah, that when we are doing our masters, we are only knowing net learn. Because all the papers we are going through, only it was a net learn. You reminded us that name.
Other place, because you mentioned military, the other place that they used our geogrids, not the uniaxial, but the square one for foundation bearing capacity improvement, was in the Falklands. And I can send you the paper on that if you're interested. So they had to extend Port Stanley Airport during the war, 1982, over peat. And they didn't have, when they did, you'll find this interesting, they did the design in London, in Whitehall, MOD, and they said, what are we going to use? Oh, yes, we'll use the sand from the beaches. There's so much sand available, no problem at all. When they arrived on site, guess what? The beaches were full of mines. They were peppered, so they could not use the sand, too dangerous for explosion. So the only thing they had to use was dune sand that they sandwiched between the square grid and only 150 millimeters of crushed rock. And at the base, peat, and then say the netlon, the same material they use in Narita Airport, dune sand in the middle, and then the runway on the top. That's a different presentation, but just for your information, because you asked.
Because you are passionate about the military engineering, so that's why I gave this example. I always give this example of military engineering. And now I can remember at that time I was in school where that war was there. So that's why I remember that. Thank you. And actually, I had some code like that LECA when you were talking about, your only unit weight is around 3.5, but your phi value is very high. So I had a doubt about their porosity. Maybe they are porous. Are they porous?
Yeah, it's porous. I showed the cross section and it's full of holes inside. Yes, it's very porous. That's why it's so light. Yes.
So that's another advantage I can think of. We don't need a drainage layer itself that can act as a drainage.
Yes, absolutely. You don't need a drainage. Actually, I'll tell you a secret. The reason why we use the drainage behind the blocks is not really for drainage always. It's a buffer zone. So the compaction is not going to get too close to the face to move it. So it's like another safety construction serviceability measure. Yeah.
That's one. Another one, you are talking about pH. PFA pH is there, but we have now some material pH is around 11.5.
Yeah, we can still do it because our pH covers 2 to 12.5, and this is on the BBA certificate. So it's because it's the same material they use in landfills, HDPE. So if it's more than 12.5, and I don't think we've ever I've been with Tensar for 15 years. I don't think we've ever had to factor it down for extreme pH. It pretty much covers, yes. And this is what I said. And the reason why we want this job in the PFA 11.5 meters was originally they had polyester geogrid, but polyester geogrid and PFA don't really go together because it's very aggressive. So they went, you know, they can do it, they can factor it down, but then they lose the benefit of the cheaper price. So like I said at the beginning to the first question, don't look product per product, look at the whole picture and see how it all compares. Yes, it's a mindset, isn't it?
Yeah.